Good morning again, team. We're getting towards the end of our journey through the realm of gases. Again, remember, gases are the easy state of matter. It's the liquids and solids that are going to be rough. So we'll save that for second semester, at least for me. Some places they'll probably include that in first semester general chemistry. Sometimes they'll wait till later. Whatever. Most people are going to take both semesters anyway. So I picture first and second semester general chemistry as one class with a really long weekend in between, right? So you need that break in between just to rest your brain a little bit. Just like, oh, I've been inundated. Not like you have other classes as well on top of general chemistry plus general chemistry lab. You're probably taking physics and a physics lab and even probably a math or a calculus and probably like an English class and a literature class. And it just never ends, does it? It does end. And as you get older, you tend to forget how painful those years was. And then you actually look at those painful years of college as nostalgic, going, wow, it was so nice to have, only, earn enough money to at least for me, I was paying for it myself. So I just make enough so I could eat. I lived on potatoes for many, many years. Pay for my classes, study, I didn't have kids at the time. Some people, holy moly, how do you, if you have kids and you're going through college, I am not worthy. I don't know. I got 4 kids. It's real hard to just grade, let alone study and comprehend concepts. So, rock and roll, gang. All right, got distracted again. I hadn't even started. So diffusion and effusion, a couple of properties of gases. We already sort of talked about diffusion. I think most people, even young kids, have a general concept of that. Very commonly, you'll see, someone will take a glass of water and put an eyedropper of a dye, food dye coloring or something, and you see that food dye hit it, and you just see it go shoo, and you can watch the liquid particles, diffusing through, and the color, it doesn't just sit there, it diffuses out. And you can't see the motion, but you see the results of the motion that's going on. Well, same thing with gases. Commonly we can't see, although I guess we could take a colored gas, nitrogen dioxide or something, and mix it with a colorless gas. Say we had 2 different chambers like that were connected by a pipe or something, and then had sealed pores that we could open up. And, let's say you've got, a colored, maybe NO2 here, a colored gas, and a colorless gas, maybe helium or something. And they're just moving around, the lighter one's moving faster. Let's say they're at the same temperature, but we learned from the last video that lighter molecules, smaller molecules, move faster. But if we open those ports and allow the gases to move, this looks a lot like my number 3 daughter, my third youngest, oldest number 3. Okay, so anyway, the third down the ladder, right? She had a pet frog, Frankie the Frog, and he had a tank that looked just like this, right? So he had one here, and he had this little connector port. It looked exactly like that. And he'd be like, bloop, bloop, and he'd go back and forth. I don't know why I told you that. It just looks like it. So anyway, as long as these are sealed, they're stuck in there, moving around in constant random motion. That was the first postulate of kinetic molecular theory, right? But if we open those ports, now what if we have a gas molecule, that if we open this up, and let's say this, bangs off the wall here, comes around this way, goes boom, 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 and we open that up, boom, and comes out that way, right? So it collides off the wall here, creates pressure, collides there, creates pressure, collides there, bang, bang, and it comes through. It's going to, sooner or later, it'll enter there, and then it can come back and go back and forth. The lighter ones will move faster, so they'll diffuse faster than the heavier ones. But over time, you will get a homogeneous mixture on the other side, an equivalent mixing. If this is colored and that's not, you can actually see the color here diluting. If this was colorless, now they're both exactly the same light shade. In this case, that pukey orange color, the smog color, the NO2. And that's just general diffusion, just the migration of gas particles due to that constant random motion. They're got the mean free path, the distance between collisions, so they don't go in a straight line forever. They go bang 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 bang, and it might come back, may stay over there. That's ultimately what you'll get. All right. So just a review of diffusion there, but let's look at a similar kind of the evil cousin of diffusion, effusion. Let's have a look at what that is. Let's take a look at effusion now, which is very similar to diffusion. Okay, so diffusion, typically people just think of 2 gases mixing together. right? Evenly, then they're evenly distributed throughout. Effusion's a slight twist on that. So let's say we got that chamber, maybe the net result of after those two gases diffuse together, we got that one chamber with the two gases evenly mixed throughout, having a homogeneous mixture, aka a solution, right? But now what we'll do is connect that to an evacuated chamber, and we'll drill just a tiny little hole. We call that an orifice, right? Think of the same thing like on filter paper. So effusion is the passage of those gas particles that are moving around in constant random motion through that orifice, usually into an evacuated chamber, right? Gases like to go from higher to lower pressure. Well, the green ones, imagine the green part, whatever they are, those are gas particles of a larger gas. Let's say they're all at the same temperature. It kind of need to be, they're in the same chamber. And then the purple ones are a lighter gas. Again, maybe, helium versus krypton, or water vapor versus, uranium hexafluoride gas or something. Obviously, the smaller ones diffuse faster because they move faster, right? They're moving faster. So what will happen over time is they'll bounce around and get through the hole, right? And the smaller one, as long as that hole's big enough for all the molecules to get through, whether they're molecules or atoms. So what's going to happen, let's say a small amount of time goes through and 3 of the small ones get through, but only 1 of the larger ones get through. Right? So they're moving through to the other side, but there'll be more particles of the smaller one than the bigger one. And we could actually measure the rate of that. We could measure how fast they're moving, time it for 60 seconds, see how many particles get through, as long as we have a good detector device or something like that. So that was studied by Thomas Graham back in the mid-1800s, right? In the mid to late 1840s, something like that, which is still amazing back then. That's like pre-Civil War. Wow, that they're studying this kinds of stuff and that they can. It truly astounds me. The history of this stuff is fascinating. Wish we had more time to read all of the history and really appreciate what was going through these people's brains and that they were able to technically do this. So let's take a look at what Thomas Graham was studying and an equation he derived, of course, named after him now, Graham's law of effusion. Woo-woo! Some people call it Graham's law of diffusion. He had some issues here and there, but we use that for effusion today. So let me write that up on the board. But now you kind of know what effusion is. And you can use this even if you want to think about isotopes, right? Because isotopes, they're atoms of the same element, so they react the same chemically. You can't separate them chemically. But the heavier ones that have more neutrons, right, you have a physical difference. So they move faster. They have a slower, the smaller ones have a faster speed, and the bigger ones have a slower speed. And so the smaller isotopes would effuse faster. So if you think about this, if you could create some kind of machine that allows effusion of isotopes, the lighter ones will get through more. So you'll get some of the big ones coming through, but you can concentrate the lighter ones in here and then maybe do it again and again and again and again, right? Like filtering something over and over and over. And you can really, really increase the amount or concentration of the lighter isotope, right? Or remove the bigger one, but you can separate them in time, right? Like for uranium or something, you want to make nuclear material. I think uranium-235 is the one you need for nuclear reactors, and one uranium-238 you don't. Unfortunately, uranium is mostly uranium-238, so you want to enrich it in uranium-235. This is something you could do to do that, right? Because the uranium-235, the lighter one, imagine the purple one is uranium-235 and the green one's uranium-238. Guess what? You got more uranium-235, and you do that a lot, you might be able to enrich it enough where you can make some nuclear grade material and run a nuclear power plant, or, for worse purposes, make a nuclear bomb out of that or something. Ooh! So just, so one kind of application you could use this for, but, use your brain on it. Let's look at the law. I ran out of space, so we'll do this in 2 boards here. But to give you the long-winded, painful version of Graham's law of effusion, right? The effusion rate of gas particles is inversely proportional to the square root of their molar mass. Now, on the next board, I'm just gonna say throw up. I'm just gonna throw up or put up on the board the equations we got from kinetic molecular theory on speed and things. Remember, that was dependent on the temperature and the molar mass. And if you've got a sample all at one temperature, then it really is dependent on the molar mass. And what was that equation? Square root of 3RT over the molar mass? Can you see where it's the rate? So speed, you can think of the rate of diffusion, rate of effusion, the velocity. All of those are kind of proportional to each other, and they're all inversely proportional to the inverse of the square root of the molar mass of that species. So the lighter the particle, the faster it goes. The heavier the particle, the slower it goes. So you can take this mass and just write it mathematically, the effusion rate, insert velocity, diffusion rate, is proportional to 1 over the square root of the molar mass. Okay? So Thomas Graham, mid 1800s, 1840, depending on your source, I've seen 1846, 1848, so somewhere in that range. So still a long time ago, right? So let's look at an application. I want to kind of derive a formula we can use to be able to measure the rate of effusion of a gas compared to another one. Or, because this is dealing with molar mass, maybe we could solve if we took two gases and we knew the effusion rate of one of those gases, and we knew its identity, and we had an unknown gas, and we measured the effusion rate of the unknown gas compared to the other one, same temperature, same conditions, we could solve for the molar mass of the unknown gas. Oh, so you could find out the identity of unknown gases using like effusion rate races. Put two gases in there and put them up against each other, right? The lighter one should effuse faster. I mean, you could qualitatively just go, hey, this one effuses faster, so it's lighter. This one effuses slower, so it's heavier. Pretty easy to do, but we can put mathematics to it and identify unknowns or actually calculate effusion rates of a known gas compared to one that we already know. You wouldn't even have to run an experiment. Sweet! Let's do some stuff. Watch the derivation here. Follow with me. Would you agree? So if we're comparing two gases, let's have a foot race between two different gases. One's heavier and one's lighter. So let's just call one of them A, one of them B. Doesn't matter which one's heavier or lighter. Let's take the effusion rate of A over the effusion rate of B. Let's take the ratio of those two. Well, isn't it based on its speed, right? So remember from kinetic molecular theory and all that stuff. Well, we use because we have a distribution of gas particle speeds and whatnot, so we use the root mean square speed to represent a sample of gases at a particular temperature. Yeah? So the effusion rate of A, we could just use the root mean square speed of A. And for the fusion rate of B, we can use the root mean square speed of B. Well, what was that equation for the root mean square speed? Square root of 3RT over the molar mass, right? So the root mean square speed of A will be 3 times the gas constant, 8.3145 joules per mole Kelvin, times the Kelvin temperature over its molar mass. And then the root mean square speed for B on the bottom, square root of 3RT over the molar mass of B. That's a little messy there, but remember, these are two gases in the same chamber at the same temperature, so 3R and T are all constants. All right, so what I'm going to do is I'm going to flip this up, right? So I'm dividing by this, so if I flip that up, I can and put them both under the square root. This would be that is the same as the square root of 3RT over the molar mass of A in the numerator, but I'm going to flip the denominator up, so I get the molar mass of B over 3RT. So you just flip it up. So now it's a little easier to see. Can you see the 3RT canceling out? So 3RT, since they're both at the same temperature will be constant, cancel out. So you're just left with the square root of molar mass of B over molar mass of A, which is the inverse. So the ultimate way most people look at Graham's law of diffusion is the effusion rate of a gas A over the effusion rate of gas B, or the ratio of the effusion rates, is equal to the inverse ratio, take the square root. So the square root of the inverse ratio of the molar masses. Oh, look at it. You just kind of do it and go, well, wasn't that nice? So I'm sure Thomas Graham was like, sweet, I'm now immortal in the realms of chemistry forever. Woo, woo, woo. In science, Graham's law of diffusion, baby. So we can use that to identify unknowns. All right? So we can, that's a big hint for a future test there, can identify unknown gases. Yay! So if I gave you the effusion rate of A over the effusion rate, if I gave you these two or just the ratio of the two, and you know the identity of one of them, you can solve for the molar mass, and then from that figure out, well, maybe that's NO2, maybe it's CO2. You could probably come down to maybe a choice or two. Or I say, hey, an unknown gas is a noble gas, and then you just calculate the molar mass and be pretty easy to peg it. Or maybe it's a halogen gas, right? So, they're diatomic, Cl2, F2. It's got to be one of those. Or if I know the identity of the two gases and I give you the effusion rate of one of them, you can theoretically calculate the effusion rate of the other one. 4 variables, right? These two are pretty easy to do. Let's do an example problem. One of the two types of problems, either I'm going to have you solve for a molar mass or I'm going to have you solve for an effusion rate. That's it. So I'll do one of the two here. I'll leave the solve the molar mass for the test, because Coach loves those kinds of questions where you solve for a molar mass, like with the gas law stuff, where the ideal gas equation where we inserted the molar mass in there. I love it when you solve for the molar mass and solve for an unknown. It's good stuff. So anyway, let's say somebody runs an experiment under some conditions, a certain temperature with a certain orifice size, etc., all that kind of stuff, right? And they find krypton gas. It takes 89.8 seconds for a certain amount of krypton gas to effuse from a chamber. So its effusion rate is 89.8 seconds. All right. Well, how long would it take for carbon dioxide gas to effuse out of? And the assumption here is under the same conditions, right? Same temperature, same chamber, blah, 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 blah. So we have to make those assumptions here. So we know the identities of both gases, so we would know the two molar masses. We know the effusion rate of one of them. We should be able to solve for the effusion rate of the other. Pretty simple. So let's do the ratio here. Now, you can do, it doesn't say what gas to put in the numerator and what to put in the denominator. It doesn't matter. To make the math easier, though, I like to take the one I'm trying to solve for and put it in the numerator. It makes it easier to solve for, because if you put the unknown in the denominator, then you got to inverse a bunch of junk, right? So since I'm solving for CO2, I'm going to put the effusion rate of carbon dioxide on the top and the one that I know on the bottom. You don't have to do that, right? If you flip that the other way, don't worry about it. You'll get the same answer. It's just one's mathematically easier than the other. Try to get the unknown in the numerator. So that should equal the square root of the inverse of the molar masses. That's Graham's law of diffusion, right? So let's do a gigantic square root signal. Since I put the krypton on the bottom, I'm going to put the molar mass of krypton on the top. And since CO2 is on the top, I'm going to put the molar mass of CO2 on the bottom. There you go. Right? The effusion rates are equal to the inverse of the molar masses. So we know this, right? Would you agree? We can solve for the molar mass of carbon dioxide. 12.011 plus 15.999, 4 times 2, good to 3 decimals. Krypton, don't have that one memorized. Sorry, gang, we're going to have to look that one up. Cat hair in the nose. Arr! We know this. Do we know the effusion rate of krypton? We do, 89.8 seconds. So really, because we put that in the numerator, just multiply the effusion rate of krypton on both sides. So this should be pretty easy to do. Let's bring this down. So the effusion rate of CO2, which is what we're trying to solve for, move the effusion rate of krypton over, times this quantity here, the square root of the molar mass of krypton over the molar mass of CO2. There you go. So that's 89.8 seconds. Look up krypton, look up CO2. See if you can pause this. I'm not going to squish it. I'll erase the board and continue this on the next board. So I'll do it myself. You do it yourself. And let's see if we match at the end. Right? Grab your trusty periodic table. You should, if you haven't printed this out by now, what are you thinking? At least if you're in my class. If you're in a different class, use the periodic table of whoever's teaching your class. Right? So each coach has their little idiosyncrasies. I've coached softball and baseball long enough to know, well, most of the fundamentals are pretty much the same, right? But some people got, they like to steal this way, or they like this particular signal, or they like the catchers to do this particular thing. And, some like to try to throw a runner out at first if they're leading off. Some don't, for the younger. Whatever. It's all fundamentally the same. We're all going to get the same answer at the end. Just how we approach could be a little bit different. I'm a little more of a stickler on using all of the decimal places, right? Because I'm like, hey, if you got oxygen, you got to use 15.9994 just so you can say 9994. Some people say use 16. I just want to smack myself using 16 because you're chopping off all those decimal places and significant digits. Somebody spent a lot of time trying to figure out, but whatever. Use whatever your coach is giving you at the time. We good? So pause it. See if you can solve this problem for me. Let's think qualitatively about the problem first, right? So if we look at the molar masses, let's figure out which one's heavier and which one's lighter. So krypton, if you look over here, is 83.80, right? 83.80. So carbon dioxide would be 12.011 plus 15.9994 times 2. Good to 3 decimal places, limited by the carbon. Right? So I rewrote that equation. So the effusion rate of CO2 is the effusion rate of krypton times the inverse of the molar masses. Let's plug in the effusion rate of krypton. Molar mass of krypton, 83.80. Molar mass of CO2, 44.0098. And you could use Dalton's or that mu symbol, the atomic mass units, or you can use grams per mole. It doesn't matter. The units are going to cancel out like so. And you'll end up with whatever units are here. No need to change them. But would you agree carbon dioxide's lighter almost by half, right? Not quite, but it's a lot lighter than krypton, which means it should move faster. Would you agree? So if it takes 89.8 seconds for krypton, it should be moving a lot faster, right? So its effusion rate should be a lot higher. So, not quite twice as high, but higher. No need to do this step, right? You've got 3 sig figs there, 4 there, 1, 2, 3, 4, 5, 6 there. Carbon dioxide was good to 3 decimals, right? So I need that dashed line. So let's put that dashed line here. Not necessary per se, because we're limited to the 3 here, but the carbon's 12.011, so really we should put a dashed line after the 3rd decimal place. Depending what periodic table, right? So some might have, different number of decimal places. Some professors don't have you track sig figs in molar masses either. Whatever. So I just wanted to show you what that value was under the square root sign, okay? So that ratio is about 1 point. So it's going to be, carbon dioxide's about the square root of 2-ish faster. Right? So 89.8 seconds times the square root of 1.90412, good to 3 sig figs is 123.91 seconds, rounds up to 124 seconds. So much faster effusion rate for CO2, which you would expect because it's lighter, but you can kind of get a rough guess. Is it going to be, 50% higher, 100% higher, just by comparing the molar masses in your mind. So it's a pretty simple law, easy to do. Let's move on. We got one more video to go. Oh, we're done with gases.